Hello guys! So over the past few years I have repaired and modified tons of used and often broken equipment that I had bought from scrapyards, thrift stores and online marketplaces. And around 4 years ago I had retrieved this old dinosaur of a power drill from a dumpster. In episode 19 of my Scrapyard Repair-A-Thon series I covered the overhaul of this two-handed Fein brand drill and used it to drill a bunch of holes in wood. That episode is linked under this video. Even back then, the idea had come up to convert this very high quality, yet rather unwieldy machine into a mag-based drill for metalworking. This year, 2024, was then mostly spent taking major steps in upgrading my workshop by tackling a number of big game-changing projects that I had quietly collected the parts for over many years. Like for example, obtaining an AC TIG welder for aluminium welding, repairing an industrial-grade water-cooled plasma cutter, building a CNC table for that plasma cutter, building a CNC milling machine, and also the construction of a gantry and the purchase of a conventional milling machine and additional tooling. Among all these endeavors, one of the biggest projects was the construction of this CNC table that I built almost exclusively from scrap. However, this project required the drilling of a ton of holes through heavy and rather unwieldy workpieces that are basically impossible to work on in my drill press. Heavy handheld power drills were employed to drill holes of up to 16 mm in diameter, but it goes without saying that this pushed man and material to the limit. And even though the CNC table is operational in principle, it is still held together with screw clamps in many places and has been waiting for further modifications and upgrades for months. In order to continue the work and for this machine to unfold its true potential in the future, a magnetic-based drill was required to move forward. So I kept my eyes open for the parts required to build a drill with a magnetic base. Years ago I found this massive transformer core on the scrap. Strictly speaking, it was used for a choke rather than a transformer, but that doesn't really matter here. Fact is that it is quite comparable to your typical microwave oven transformer core, but roughly 4 times its volume and mass. You don't see that every day. But key components were still missing, and I wasn't sure how to go about this, when by mere chance a few weeks ago I stumbled over just the right piece of equipment on this scrapyard here. An attachment for an old Fein brand core drill, only without the actual drill that you can see in this picture here. In case you don't know what I mean, this is a type of setup used for drilling holes through concrete walls, like you see here. So I bought this thing and brought it to the workshop. It has been modified in at least 2 ways. The first modification is this pretty rugged steel support that was professionally fabricated for this attachment. It looks like the former owners might have used it as a drill stand in a workshop rather than for its original purpose. However, we don't need that support, and that's why I'm removing it using an impact driver. We also won't need those bolts here, and that's why I'm removing them as well. This rather massive steel part that is supposed to attach to a really big drill is also a modification. It was apparently made in a professional machine shop, probably to hold a machine with a bigger collar than what it was originally made for. It's pretty rusty and I'll take care of that in just a few minutes. However, for now I'm simply trying to clean everything and think about how exactly I will combine all the components to build a mag-based drill. The first question I had was if this Fein brand attachment would actually go together with the Fein brand two-handed drill we found and repaired 4 years ago without ever really using it since. To really put this machine to work, I had also purchased an adapter from Morse taper number 3 to 3/4 inch Weldon shaft, which will allow me to insert big arbor drill bits like this 20 mm arbor that I will need to finish the work on the CNC table. And I got really lucky here since, ta-da, the old drill fits our improvised drill stand just perfectly. So let's see if we can cut 20 mm holes on a piece of scrap then. So this tells me that this setup could actually do the job that I need it for. Now we have to figure out how to turn this drill stand magnetic. Now, this particular type of core is often referred to as an EI core because it consists of E and I shaped pieces of transformer lamination. The lamination technique of high permeability steel sheets, which are electrically insulated from each other, is employed to minimize the losses caused by eddy currents that are being induced inside the electrically conductive parts of the core. However, this is only an issue when using alternating currents. But since we will use direct current instead, lamination wouldn't have been necessary. A solid piece of steel would have been sufficient. However, the high permeability steel and specific shape of the E part of the core is still ideal to build a powerful electromagnet. And when I first found this core on the scrap, I made this bobbin or coil former with a 3D printer because I knew that it would be used one day. The form of the bobbin is very crude, however, since it was one of the very first 3D printed parts I ever designed when I got the printer a few years back. Normally, transformers, chokes and also electromagnets are wound using stiff magnet wire that is coated with a thin layer of insulation. But it is very hard to bend wire with sufficient cross-section area by hand without damaging the bobbin. And that's why I will do it with ordinary flexible wire, just like almost anyone else on YouTube. And it's kind of hard to say how many turns we will ideally need, but since I have adjustable power supplies galore, we will simply try to fit as many turns as we can with this given size of copper wire on the core. And since the workshop is currently undergoing a major transformation, a lot of my electronics test equipment is not accessible at this point in time. And that's why the first test of the magnet was performed using other scrapyard finds. I soldered a tab roughly onto the midpoint of the secondary winding of this old 12-volt toroidal transformer. It connects to a full bridge rectifier that I bolted to a salvage CPU heatsink. This clamp meter will measure the alternating current flowing through the secondary winding of the transformer. The steel plate that I leaned close to the core is attracted to the core with tremendous force. And you don't want to get your fingers between those parts. 16 amps at roughly 6 volts AC secondary voltage is a little on the high side. You could maintain this for a good while, but the coil would probably overheat after some time and the insulation would start to melt. Now, I have seen professional mag bases that run the coil at close to 200 volts DC, derived from the mains voltage without a transformer. In that case, you would have to use much thinner wire with way more turns, or otherwise the current flowing would be gigantic. The coil that I wound here could be replaced at any point in the future. But at this point in time, I simply didn't have access to much of my equipment and was happy about any solution that simply worked, practical or not. But some of you might wonder how this even works in the first place. First of all, in the case of this core, the moment you remove the I-shaped section, the magnetic circuit is opened. There no longer is a closed high permeability path, which will weaken the magnetic field density tremendously. The moment you bring a piece of mild steel close to the core, it snaps in place and closes that magnetic circuit. In fact, a piece of steel with the same magnetic cross-section as that eyepiece would have been better. Or in simple terms, this piece of steel is too thin. Ideally, it would be at least 4 times as thick. And since the E-shape of the core might be confusing to some viewers, I bet you all have seen horseshoe-shaped magnets or even straight ones. But how many poles would a 3-pronged magnet have, and where are those poles? Well, I spent some money so that I would be able to have the means to visualize this for you and show you. Let's have a look. So what you can see here is that the middle limb of the E-core clearly forms a strong magnetic pole. But upon using this flask filled with ferromagnetic fluid, we can see that the 2 outer limbs likewise form magnetic poles. But they are weaker since the magnetic cross-section of the 2 outer limbs or legs is only half that of the middle limb. Their ends are also further away from the coil, of course. And the classic experiment, iron filings. The iron filings roughly align with the magnetic field lines. These lines always occur in closed loops. They travel through the entire core and split off into the 2 outer limbs. Then they travel through the air and enter the core again, closing the loop. The magnetic poles are simply the very spots where the magnetic field lines exit one medium, the steel, and enter another, in this case air, and vice versa. But be that as it may, it's a strong magnet and I think it'll work as intended. So we basically have a stand and a magnet, but simply installing the column on top of the magnetic base won't work because the magnet is so tall that the tip of the arbor would never even reach the workpiece. So you guessed it, and it's the story of my life. We have to make things somehow fit together that were never meant to. In this case, I decided to modify the steel block that holds the power drill. In order to make it all work, the old part has to be separated into two sections. And my first idea was to do that with the new milling machine. But I decided to go easy on that machine instead and cut the piece in half with an angle grinder. But since cutting things with a grinder doesn't exactly create nice straight surfaces, the milling machine was used in another capacity here after all, in milling the faces of these parts. And while doing this, I sprayed large amounts of cutting oil onto the workpiece manually, a common theme throughout this video. I already have a coolant pump, but it's not installed yet. See, if you build, maintain and repair your own machines, there is always the need for upgrades. But at the same time, you also just have to make things happen on a daily basis. But now that we have these nice machined surfaces, it bothers me even more how nasty the rest of it looks like. And that's why I prepared an acid bath next. The speed of the rust removal process with citric acid is really dependent on the temperature. In this case, under a blue August sky, you can actually watch the rust disappear almost in real time. So while those parts are sitting inside the citric acid, we prepare a bunch of other parts that are needed to actually fasten the electromagnet to the drill stand. For that, I first made a CAD drawing of a square with rounded corners, which was then cut out from a piece of scrap using the CNC plasma cutter. It fits right onto the transformer core. The column of the drill stand will be welded onto it. And we won't weld anything directly to the core because it's not a solid piece of metal, but rather thin sheets glued together. But luckily the core has a number of holes that can be used to bolt it down. And in order to make use of that, we cut 4 angle pieces of equal length from this piece of stock. And this is where they will be installed. However, first we needed to drill holes into those sections and weld them to that plate sitting on the top side of the core. In the meantime, I had also designed and printed this custom-made part here that is supposed to allow us to not only hold the drill by its collar, but also give additional stability by using this bolt to fasten the drill to the stand as well. I might later decide to make this part from metal instead using the milling machine, but I first wanted to have a positive that would actually fit this rather complex surface of the drill. In the next step, the column was then shortened by a few centimeters using an angle grinder. It was necessary to do this so that we can actually reach the workpiece with our drill bits. And after that, we proceeded by welding it to the plate that is bolted to the magnet's core. This took way longer than can be seen here in this video, because I had to make sure that the parts are as square as possible. If we don't have 90 degrees in every direction here, then well, the holes that we're going to drill are also going to be slanted. So column and base are now firmly connected. But in order to attach the machine to the stand, we had to continue the work on the parts we separated before. In order to join them again, 2 square pieces of steel of equal dimensions were cut out with a plasma cutter. The 2 parts were then welded together. I did this because I needed something thicker than say 8 or 10 millimeters, but there are limits to the thickness of material that my plasma cutter can cut. And I won't lie to you, one downside of picking random pieces of steel from the scrap is that you sometimes don't exactly know what you are working with. And this particular stock didn't really make for smooth TIG welding. But it'll hold just fine. The welds are just not as pretty as they could be. This newly created part is now joined with the piece that is supposed to hold the drill's collar. This again took a very long time and a lot of preparation and measuring to do properly because I want this part to be properly aligned. And after this piece had cooled down, the milling machine was then called to action once again, this time to cut a big hole that bolt will go through in order to fasten the drill up here as well. You could do that with a drill press, but then again, I don't have any 30mm drill bits yet. After having done that, I was now able to clamp the drill into this new part and attach it to the stand using a screw clamp. I did this to align these parts and see if everything would work out as imagined. And as you can see, there is still about a 5mm air gap between the printed part and the steel, and I might have to print a thicker version of it to compensate for that. But other than that, I was satisfied and proceeded to weld the parts together. And now it was time to see if this contraption can actually do what it's supposed to. Moment of truth. Okay, so the magnetic drill passed its first test, but it's all good for nothing if I can't use it to actually work on my CNC table. See, when I was first working on this table, there was supposed to be a 20mm bolt sitting in this spot, and I've been waiting to do that for at least 2 months now. So let's finally make it happen. And let's repeat the same thing on the right hand side of the table as well. And let me tell you, it feels really good to finally put these bolts in here. For the next step, the linear guide assembly of the X-axis has to be lifted off the table. Its combined weight is around 120 kilograms, and that's why I have to employ the gantry that I built in the last episode here. This also shows you that I built this gantry so that it would actually fit around the table. And after lifting off the big guide and screw, I can now also push the trapezoidal screws and guides of the Y-axis to the side to be able to finally drill the holes that are supposed to hold these assemblies. See, when I first set up this table, it was the most important thing to align the different guides correctly before determining the precise spots where the holes needed to be drilled, which I'm now finally doing. And in order to use ordinary drill bits, the Weldon adapter was swapped out for an ordinary chuck. After punch marking them first, I decided to pre-drill these holes before then actually using the 10mm drill bit. This was repeated 8 times on each side of the table. So all in all, I drilled 16 10mm holes on top of the 20mm holes you saw a minute ago. I really like how well this works, and considering that this is what the machine was made for, I would call it a success. As mentioned before, with regards to the milling machine, a cooling pump would be nice here as well. And even though the use of a heavy lab power supply is not that practical, it is actually a fantastic feature to have to be able to adjust the current when you just want to reposition the magnetic base, or even just move it a tiny little bit to correct, the spot where the drill bit is hitting the metal. The same feature could be implemented using a much smaller power supply and an adjustable buck converter, for example. And I should absolutely build that to make this machine more practical to use. So guys, that's what I had in store for you today. I hope you liked this video, and I would like to ask you guys to leave a thumbs up if that was the case. I would really appreciate that. And in case you want to support me in producing more videos, it would also help tremendously if you would consider making a donation. A link for that is under the video. Or if you would become a supporter on Patreon under patreon.com/tpai. See you soon.